Hi class, Mr. Morris again. We're continuing our notes on periodic trends. We've got some example problems that we're going to go through. If you want to pause the video with each of these and try it yourself, that would be a great idea. In fact, I'm going to say you don't have to watch this whole video. You can actually just try the example problems, compare your answers to the key that I'm going to put out there, and if you get the same answers and don't have any questions, that's fine. This is more for if you need an in-depth explanation of one of the problems. Skip ahead to what you need to see and just use it like that. So example explanations for periodic trend comparisons. We're starting with up and down a group. And the way you know it's up and down a group is because in this case I'm comparing sodium and potassium. And if you just look, sodium's right here, potassium's right under it, so we're going down a group. The potassium atom has, let's see, how many shells does it have? 1, 2, 3, 4. It's in the 4th energy level, and sodium's in the 3rd. So we could say potassium has 4 energy shells, sodium has 3 energy shells. So that means potassium's valence electrons are further from the nucleus than sodium's valence electrons. So potassium's atomic radius is larger, or you could say greater, than sodium's atomic radius. And that would be a sufficient explanation for why potassium's atomic radius is larger. You've got more energy levels, that makes a greater distance between the nucleus and the outermost electron. If we're comparing the ionic radius, same thing is still true. Potassium plus, now in this case it's kind of interesting because K plus actually has 3 energy shells because we lost that outer energy layer, right? But sodium plus has 2 energy levels, or energy shells, because it lost that 1 electron, so we go down to the previous energy level. Potassium plus's outermost electrons are further from the nucleus than sodium plus's outermost electron. And as a result, potassium's ionic radius is larger than the sodium ion's ionic radius. All right, let's go down, and I'm going to zoom in a little bit more. Okay, comparing first ionization energies. The reason we say first ionization energy, that's the first electron that you take away. And when we talk about ionization energy, we're usually talking about first ionization energy. Okay, the ionization energy of sodium versus potassium. Well, potassium has how many energy shells? It's got 4, and sodium has 3, right? It has 4 energy levels. Sodium has 3. So potassium's valence electrons are farther from the nucleus. Does this sound repetitive? It should. But I want you to understand that this reasoning works for all of the trends to some extent. Since it's further from the nucleus, the attractive force, remember, the distance, the farther away something is, the weaker the attractive or repulsive force between those two objects. So the attractive force between the nucleus and the valence electrons in potassium is weaker than the attractive force in sodium. Thus, it will take less energy to remove valence electron from potassium than it would from sodium. That's why we have a lower ionization energy as you go down a group. Then we get to electronegativity. Now we want to look at nonmetals usually if we're comparing electronegativity, because this has to do with covalent bonds. Okay, now let's compare chlorine and bromine. So chlorine is here and bromine is here. Chlorine's in the third row, bromine is in the fourth. So chlorine, it has 3 energy shells. Bromine has 4 energy shells. All right, chlorine and bromine. Yes, chlorine has 3, bromine has 4. Chlorine's valence electrons are closer to the nucleus. Than bromine's valence electrons. That means the attractive force between the nucleus and the valence electron in chlorine, because it's closer, the attractive force between the nucleus and the outermost valence electron is stronger than it is in bromine. Thus, chlorine will be able to attract shared electrons more strongly. Than bromine will. That means it's got a greater electronegativity. And we'll continue on. The next part we're talking about if you're going across a period. Across a period, you use different explanations. So you notice up here, we're always talking about the number of energy levels. As you go down a group, you're talking about the number of energy levels, because that changes every time you get a new row. And we're always talking about the distance from the nucleus, because as you get more energy levels, the distance increases. Down here, the energy level stays the same, so we can't use the number of energy levels to explain these trends. We're going to be comparing across a period, so we need to explain this a little bit differently. So let's start with atomic radius. Looking at the atomic radius of sodium versus the atomic radius of chlorine. Let's look at where they are. Well, sodium is here in the third row, and chlorine, you'll notice, is also in the third row. So they're in the same row, same number of energy levels. We got to look at what is actually different. So same row, same number of energy levels, but the number of protons is increasing. So let's compare. The chlorine atom has, again, we're looking in the third energy level. The chlorine atom has 3 energy shells, and the sodium atom has 3 energy shells. That's the same. Okay. Chlorine has how many protons? Well, it's got, I think it's 35, right? No, that's the mass, I'm sorry. It's got 17 protons. Sodium's got 11. So chlorine has more protons than sodium. Same number of energy levels, but more protons means a stronger pull on the nucleus. So the attractive force between the nucleus and the valence electron in chlorine is stronger. That attractive force is stronger than the attractive force in sodium. So chlorine's valence electrons are more attracted to the nucleus than sodium's valence electrons. They're more tightly bound to the nucleus than sodium's. So chlorine's atomic radius, because they're more attracted, that outer layer of electrons is more attracted. That means they're going to be pulled in closer. And remember, the radius of the atom is defined by how far away the farthest electron is. If it's attracted more strongly, then those electrons are pulled in, and chlorine's atomic radius is I don't know why it's not letting me zoom. I'm sorry, guys. There we go. Chlorine's atomic radius is smaller than sodium's atomic radius. By the way, where I said it's more attracted to the nucleus, we could just as easily, because we kind of already said that, we could just as easily say that they are closer to the nucleus. And that would be a great explanation too. Comparing the ionic radius of sodium plus and magnesium 2 plus. Now we're looking at two positive atoms, but they're right next to each other. So magnesium 2 plus and sodium plus. So I have those two right next to each other. Magnesium has 3 energy levels. Sodium 2 plus has 3 energy levels. Actually, technically we lost 1 energy level because remember they lost their valence electrons. They're here in the 3rd energy level, so if they give away those electrons, then they would have only 2 energy levels. But they still have the same number of energy levels. Mg2 plus has 2 energy shells. Na plus has 2 energy shells. So the Mg2 plus ion has more protons than sodium plus. The attractive force between the nucleus and the outermost electron in Mg2 plus is stronger than the attractive force in Mg2 plus. It's stronger than the attractive force in Na plus. So Mg2 plus's outermost electrons are closer to the nucleus because they're more attracted to the nucleus. They are pulled in closer to the nucleus than Na plus's outermost electrons. So the magnesium ion's ionic radius is smaller than sodium plus's ionic radius. Now let's compare first ionization energies of sodium versus chlorine. Again, they're both in the 3rd energy level, so we have 3 energy shells. And sodium also has 3 energy shells. The chlorine atom has more protons than the sodium atom because they're in the same row, but the number of protons continues to increase. The attractive force between the nucleus and the valence electron in chlorine is stronger than the attractive force in sodium. Why is that? Because we have the same number of energy levels, but we've got more protons pulling those outer electrons in. Thus, it will take more energy to remove a valence electron from chlorine than from sodium. It's hard to take those electrons away if they have a stronger pull from the nucleus. So that increases the first ionization energy. All right, comparing the electron affinity of sulfur and chlorine. So let's look at sulfur and chlorine. Sulfur's right next to chlorine. It's got 1 fewer proton. They're both in the 3rd energy level. So the chlorine atom has 3 energy shells and sulfur has 3 energy shells. The chlorine atom has more protons than sulfur because it's 1 further over towards the right. The attractive force between the nucleus and the valence electron in chlorine, so if chlorine has 1 more proton, then the attractive force between the nucleus and the valence electrons in chlorine is stronger than the attractive force in sulfur. So we put stronger right here. As a result, chlorine will be able to attract the newly added electrons more strongly than sulfur, and more energy is released when the electron is gained by the chlorine atom than when it's gained by the sulfur atom. And that's the definition, as you know, of electron affinity. It's the amount of energy released when an electron is added to an atom.